At this point in class, we've talked through a lot of different scenarios to think through where energy is stored before an event happens and where that energy is stored after the event happens. We know that depends on how we define the system and what's actually involved in the scenario. So this is a scenario with a bungee jumper starting at a high height and ending at some low height. And depending on how you define the system, either the initial gravitational potential energy gets transferred to some less gravitational potential energy and spring potential energy, or if you don't include the bungee cord in the system, then you have the bungee cord doing negative work on the jumper or the system. So the initial gravitational potential energy is less in the end. And where did that go? It was transferred out of the system, and we call that negative work. This video assumes you know how to think through these situations, at least conceptually, and represent what's going on with energy using an energy bar graph. If you need a review, there will be links in the description below which introduce energy bar graphs and walk through some basic scenarios. For this video, though, for my purposes, I want to talk through how do we actually calculate how much energy is stored or how much work is being done. For instance, how many joules of energy are stored by somebody standing at a height, some height above zero? Or if there's a bungee cord pulling on a jumper that's moving down and it's pulling up, it's doing negative work, well, how much negative work is being done? How much energy is transferred out of the system? So to help us think through that, we're going to think through a situation of somebody stretching a spring. We've already talked about in class how to figure out how much energy is stored in a stretched spring, which is, we call that spring potential energy. So let's first think about this conceptually, make an energy bar graph. We're going to define our system as the spring, and position A will be the unstretched spring, position B will be the spring when it is stretched, and it's going to have, a hand that's stretching it. So the hand is going to apply an external force causing the spring to stretch some distance. So in the beginning, if our system is the spring, and we're going to assume it's at a height of 0, so it has no gravitational potential energy stored, it's not moving, it's not stretched. So in the beginning, our spring system has 0 energy stored. Nothing in the kinetic energy account, the gravitational potential energy account, or the spring potential energy account. Well, at position B, we'll assume the spring is at the same height, and it's at rest, it's not moving. So there's no kinetic energy, there's no increase in gravitational potential energy, but it's stretched. And we know stretched materials like a spring that will go back, store what we call spring potential energy. So our system now has energy stored in the end. It didn't in the beginning. Where did that come from? Well, there must have been energy transferred into the system. And when energy is transferred into a system, we call that positive work. Well, we have to account for where that energy came from. We say there's positive work being done. The energy is transferred into the system by the hand, applying that external force. So now that we have an energy bar graph which describes what's happening with the energy, we can write our energy conservation equation. We say that 0 plus the work done equals the spring potential energy stored in the end, right? Because 0 plus work equals spring potential energy. So we can say that the quantity of energy stored in the spring potential energy account has to be the same as the amount of positive work done on the hand. Well, we already know quite a bit about the amount of spring potential and energy stored by a stretched spring, and that came from our investigation of springs. We did a lab where we looked at how much force a spring will exert as it's stretched, and our springs, and all ideal springs, will have a linear relationship between force and stretched. And we used that graph to talk about how much energy or effort is stored in a stretched spring, and we came up with this equation that the amount of spring potential energy stored, or the amount of energy stored in the spring potential energy account, is equal to 1/2 times the spring constant, that was the slope of our force versus stretch graph, times the amount of stretch or compression squared. If you need a review of how do we actually derive this equation from our spring investigation data, there will also be another video linked in the description below for you to check out. So we derive this equation by thinking through the fact that on a force versus stretch graph for a spring, the amount of area under that line represented the energy stored by that stretched spring. Well, let's look back at our energy conservation equation. The amount of energy stored, which is the area, in our stretched spring, the spring potential energy, is the same as the work being done by the hand. So this area also represents the total amount of work done on the system. Well, let's change this graph just a little bit. This is a graph of the force the spring exerts on the hand as a function of its position, but this same graph, because of Newton's third law, would also describe how the force, the external force, has to change on the spring as the spring is being stretched. Because the force the spring pulls back to the left with has to be the same force as the the hand is pulling with the spring to the right, these two things are pulling on each other, and Newton's third law says if two things pull on each other, they have to exert the same size force at any instant in the opposite direction. So the size of these forces would be the same. So the area of this graph, is the amount of spring potential energy stored, but we can see that it also represents the work done on the system. So if we think about this graph, this actually allows us a technique to solve the work done on any system regardless of what's happening to the force. So if we graph the external force on a system as a function of the position of the system, as the system is being displaced, the area of whatever that graph is will be the work done on the system. How much energy will be transferred into or out of the system. So we can say to quantify the work done on a system, you need to make a graph of the external force applied to the system as a function of the system's position, which is an F versus X graph, and the area represents the energy transferred into or out of the system. That is what we defined as work. So let's use this idea now to figure out a general equation for work being done, and we can also use this to figure out how much energy is stored in the gravitational potential energy account when masses are raised to some height above zero. So here's a reminder of what we just talked about, and let's use that idea to now think through a situation where, let's say we have a box that's on a surface with negligible friction, and we're going to define the system as the box, and there's going to be a person pushing the box with some constant amount of force over some known distance d. The box will be displaced. And if there's a force being applied, there's energy being added, there's work being done, in the end, that box is going to then store some amount of kinetic energy. So let's talk through how would we find the amount of energy added to the box, which would all be kinetic energy, how much work is actually being done. Well, let's use this graphical technique of graphing the size of the external force on the system, which is the box, as a function of the position of the box. So if a constant force is used, that of force F, let's just leave it symbolic without a specific force, it would just be a flat line, because as the box is changing position, as it's moving to some final distance d or position d, it's going to feel that same size force the whole time, assuming the person applies a constant size force. So what did we say the area of a external force versus position graph represents? We said that's the work done on the system. Right? The area is the energy transferred into or out of the system. It's transferred into the system because the force is in the same direction that the box is moving. If the box is moving to the right and the force was to the left, energy would be transferred out of the system. That would be negative work done. Well, what's an equation or expression for the amount of area? Well, we've got the area of a rectangle, so it's just height times width. The height of our rectangle is the size of the force used, and the width of our rectangle is the distance over which the system moves. So the amount of work done, which is the area, that's how much the system's energy will change, is just equal to the force applied, the external force applied to the system, times the displacement or the distance the system moves. Work is F times d. And so we now have a general equation which allows us to calculate the work done, the amount of energy transferred into or out of the system, if we know the constant force used and the distance the system moves. And this can work for a lot of situations. We'll have to refine this a little bit later in the video, but at least we've got a general equation now to figure out the amount of work done. Well, let's use this equation now to think through a situation which allows us to calculate how much gravitational potential energy something will store when a mass is raised to some height. So let's just take a book. Let's say that starts at a height of 0, so it has no gravitational potential energy stored by it and the Earth. Let's assume it's not moving, so it has no kinetic energy. So the system in the beginning has really no energy. And let's assume now a hand is going to raise the book up at a constant velocity and then raise it to some height, or it'll change vertical position. It'll have some change in height by delta y, and we'll assume it's at rest at the end. And so there's positive work being done on the book because the book is moving up vertically and it's feeling a force in the same direction. Positive work is being done. And if that book is now higher than what it was, it and the Earth store energy in the gravitational potential energy account. And if it's at rest, there's no kinetic energy. So all the work being done is stored as gravitational potential energy. So if we can find an equation or an expression for the amount of work done on the book in this situation, that will be the same as the amount of gravitational potential energy stored by the book and Earth system. So let's make a graph of the external force applied to the book system, and as a function of how it's changing position vertically. Y stands for the vertical position of the system, or the book. So how much force does this person have to use to push the book up at a constant velocity? Well, it would have to be equal to the weight of the book or the size of the gravitational force pulling down the book because of its mass. So the size of the external force used would be the same as the force of gravity on the object, or Fg. And let's just assume it's moving up at a constant speed, so the force they have to apply is the same size as the gravitational force no matter where the book is in its trip from position A to position B. So we'll assume it's a constant force applied, and that book is going to move from a 0 vertical position to some final vertical position. We're just going to call that delta y to leave it in a general form. And the area then will represent the amount of work done on the book Earth system, the energy transferred into eventually gravitational potential energy. So what's the height of this rectangle? Well, it's the gravitational force. What's the width of this rectangle? It's how much the vertical position changes, or the final height it reaches from 0. In order to figure out the size of the gravitational force on any object, you take its mass times the gravitational field strength. So in place of Fg, we just write mg. And so this would be the force of gravity times the change in vertical position. So mg delta y represents how much work is being done on the system. And in this situation, all of that work is being stored as gravitational potential energy in the end. So we now have a general equation to figure out how much something's gravitational potential energy will change if you know the mass of the object, the gravitational field strength of the planet or moon or object that you're on, and you multiply that by the change in your vertical position. So mg delta y will tell us how much something's gravitational potential energy will change. So now we've got two more equations, some tools to help us think about energy scenarios quantitatively. Well, before we're done with this video, I want to look more closely at this idea of work being done calculated by the force applied to a system times the displacement of the system. To do that, I want to think about just a simple situation where we have a fan cart that's feeling a pushing force from the air particles. The blades are pushing the air back, so Newton's third law says the air particles are pushing the fan forward. So the fan cart system, starting from rest, is going to have no energy. We'll assume this is a height of 0. And as the force of the air is doing positive work on the fan, it's going to gain some amount of kinetic energy in the end. Right? Here's our energy conservation equation for the scenario, assuming it starts at rest and that it's at a height of 0 and stays at a height of 0. All the work done on the cart is going to the final kinetic energy in the end. Well, we're going to look at 4 different situations where the fan is actually pointing at different angles. So one, it'll be pointed straight forwards, and then we're going to kind of point it off to the right. So less of that force is in the direction of the fan cart's displacement. So let's see what that looks like. So on the right here, I'm showing kind of the top perspective of the direction of the air's push on the fan cart compared to the direction of the fan cart displacement. So for the top scenario, the pushing force in the air is in the exact same direction as the system's displacement. There's no angle between those two things. We can say the angle between them is 0 degrees. And you can see that it reaches a pretty high velocity. It's got a decent amount of kinetic energy. So the final speed or velocity will give us a relative indication of how much kinetic energy the cart has, which is how much work was done on the cart as it was displaced. In each of the other examples, I rotated that fan so it pushes not in the same direction it's moving, but at a different angle. So for the second one, the pushing force from the fan is at a 60-degree angle with the direction of the fan cart's displacement, or D. The third one is at an angle of 75 degrees, and the fourth one is at an angle of 90 degrees. So the pushing force from the fan it's perpendicular to the direction the car could go. But you can see that the fan is on and the cart is going nowhere. Okay? In all 4 of these cases, the same pushing force is being applied. The external force is the same, and at least for the first 3 scenarios, they're being displaced the same amount from where they start to the right side of this video. So we said we can calculate the work being done, the energy transferred into the system, by taking the force applied, the external force applied, times the displacement of the system. But if we compare these first 3 scenarios, even though the same force is applied, they're moving the same distance, clearly there's not the same amount of work being done on each car because they don't reach the same kinetic energy in the end. All right, the one that has the biggest kinetic energy must have had the largest work done. That would be when the force is in the same direction as the displacement. And when the force is not in the same direction, we can see there's less kinetic energy, so there must have been less work done. And the bigger the angle there is between the direction of the system's displacement and the direction of the applied external force, the smaller the amount of work being done. So the work being done can't just depend on the size of the external force on the system and the displacement of the system. It must also depend on that angle. So let's look a little bit closer at scenario 1 and scenario number 2. If the force is in the same direction as the displacement, there's no angle between them, the work is just calculated by the size of the external force times the displacement, right? Because all of that force was parallel with the direction that the system was being displaced. But if we look at scenario number 2, where there's a 60-degree angle between there, not all of that force is in the direction of the displacement. There's only a smaller piece of that force or smaller component in that direction. And the amount of the force in the direction of displacement, that's what determines how much work is being done. So in our work equation, it's not just the size of the force times the displacement, it's the size of the component of the force in the direction of the displacement times the displacement that actually matters. So if theta represents the angle between the actual force and the component of force in the direction of movement, then this is the adjacent side of, you can see this right triangle, and so we can use the cosine equation to solve for the size of the component of the force. If we know the size of the actual force and the angle, so the adjacent side is equal to the actual force times the cosine of that angle. So we can replace this with just f cosine theta times d. So if there is an angle between there, it's more than 0 degrees, then we have to use f cosine theta times d. And the way that this is expressed on an AP Physics 1 equation sheet is actually this. This is the complete way to calculate the size of the force for any situation, for any angle between the actual applied force and the displacement of the system. So it reads, the change in energy of a system is equal to the amount of work being done, which is just f times d, as long as those two things are parallel with one another. But if there's an angle between those two things, then we have to add the cosine of theta term. So if we were to calculate the work being done on the fan cart for that second scenario, it would be work is equal to the pushing force from the fan, that's the external force applied on the system, times the displacement of the system, and we'd have to multiply by the cosine of 60 degrees. The last thing we need to discuss is how do we find the work being done if the force is changing in size? This equation, which we just talked about, assumes that the size of this external applied force is staying constant. But what if it's not? What if it's changing in size? So let's just think about this simple situation. Let's say a box is sliding 1 meter to the right. That's the distance it moves. And let's say there's somebody pushing to the right initially, so it's going to move the box to the right. At the initial position, let's say they're pushing with 20 newtons of force. But as the box position moves to the right, as it, let's say, gets halfway to 0.5 meters, they're reducing the size of the force they're using to move the box to the right. Okay, so when it gets halfway, it's going to be moving to the right with some velocity. And then let's say once they reach the halfway point, they actually switch to push backwards against the box, and so they're applying a force in the negative x direction. And once it passes halfway, they're pushing back with a little force, and as it continues to slide, they push with a greater and greater and greater force. And let's just assume that this force is changing linearly from positive 20 newtons to negative 20 newtons as a function of the position. Well, we can't just use f d cosine theta because f is changing. So what do we actually do? We have to go back to how do we find the amount of work being done on a system graphically, how we came up with our work equals force times distance equation. The work being done on a system is just equal to the area of a external force applied on the system versus position graph, which that's what's actually given. So how do we figure out the work being done? Well, we have to do it 2 separate times because there's some positive work being done during the first half because the box is moving to the right, it has a positive displacement and is feeling a force in the positive direction. So when we shade this in, that's a positive work. That shaded area is above 0, so that we call this a positive area. It's positive work being done. For the last half, the box is still moving to the right. It's moving from 0.5 meters to 1 meter, but it's feeling a force in the negative direction. If something is moving to the right and feeling a force in the negative direction, that's how we defined negative work. Energy is being transferred out of the system. So when we shade things in on the right side of the graph, it's got to go from whatever the force is up to the 0 axis. We're always shading in the area either from above 0 down to 0 or from below 0 up to 0. So if we want to calculate the positive work done, that's the area of a triangle, 1/2 base times height. Our base is 0.5 meters. The height of our triangle is 20 newtons, so 1/2 times 0.5 meters times 20 newtons gives us 5 meter newtons or Newton meters, and remember a Newton meter is a joule. So for the first half, there's positive 5 joules of energy being added to the box system. During the second half, let's find out the area of that triangle. It's also 1/2 base times height, so it's 1/2 times the base from 0.5 to 1 is also 0.5 meters. The height is negative 20 newtons, and so the amount of area we'd say is negative 5 Newton meters or negative 5 joules. That represents the amount of energy transferred out of the box. So if we want to figure out the total work done on the box, that would be the net work done on the box. That's just equal to the sum of all of the individual work being done. The positive work plus the negative work. In the beginning there was 5 joules added, and there's 5 joules taken away. So we would say that the net work done on the system is equal to 0 joules. So now, in addition to having energy bar graphs to think through where energy is stored before something happens and after something happens to get our energy conservation equation, we now have some equations to calculate specific amounts of energy in joules for spring potential energy, gravitational potential energy, and the amount of energy transferred into or out of a system which we call work. The only one we can't quantify yet, which we will need to, is how much kinetic energy there is stored for an object moving at a certain velocity. We're going to save that for another video or an investigative lab that we'll do later in class. Hope this was helpful.